Okay, let's start today talking about ionic bonds, because that's going to be the key for our next couple classes. So, ionic bonds. Now, refresh my memory from grade 9 electricity. Do like charges repel or attract? Yeah, they'll repel each other. What does attract? Opposite charges. So an ionic bond is the electrostatic attraction between ions. The electrostatic attraction between ions. Here, electrostatic, we're talking about positives and negatives being attracted to one another. So in saying that, what do you think ions are, if you had to take a guess? Yesterday, we talked a little bit about what atoms like to do, right? Atoms, if they have one valence electron, what do they really want to do? Talked about it yesterday. Why is the alkali metals so reactive?
Because
Yeah.
they want to pair with another one.
With another
They
crystal?
want to get another electron.
Not that they want to pair with another electron, crystal.
They only have one again, so they want to lose it?
Yeah. So all elements want to get a full outer shell of electrons in order to be, I say, happy, but really electronically stable is what I mean by that. Now, in order to become electronically stable, sodium, for example, would need to lose one electron, because if it loses that one electron, now it has a full outer shell. It has the same electronic configuration as neon. Okay? Now, in losing or gaining electrons, we are going to change the charge of that atom. So, what do I mean by an ion? Well, an ion is going to be a charged atom. Yep.
So, like if sodium did lose its electron,
Mm-hmm.
it would be negatively,
We'll talk about that in a second.
okay.
But if you lose negatives, what do you think your atom's going to do? Exactly, right? And if you gain negatives, you'll be negative. So an ion is a charged atom or group of atoms. And we'll talk about this a little bit later on when we introduce the idea of polyatomic ions, or a group of atoms bonded together. Now, don't worry about this second part right now. This group of atoms bonded together, that's technically in the definition of an ion. Now, what are the two different charges you learned about in grade 9? Positives and negatives. So ions can have a positive or negative charge. We call positive ions cations. Okay, so a cation is a positively charged ion, and an anion is a negatively charged ion. And if you're wondering why I write in all caps, my writing is absolutely horrific. So it's the only way it's truly legible for students. So you were right, Carissa, that a atom that loses electrons will become more positive. So let's explore an ionic bond through an example. And we're going to use a classic example here, right after my namesake. What atoms do you think we're going to use? Sodium and chlorine. So we'll explore this idea through sodium and chlorine. Alright, so if I were to draw out an atom of sodium, how many electrons does it have? So our neutral atom of sodium has how many electrons in it?
11.
Perfect, it has 11. So the Bohr diagram for it would look like this, right? It has 1 valence electron. How many protons are in our atom of sodium? 11. So our neutral atom here has 11 protons. We currently have 11 electrons. And this is our neutral atom of sodium. Now, what is it that our atom wants to do? It wants to become electronically stable, so how is it going to do that? Excellent. It's going to lose that 1 electron. And again, why is it that it doesn't want to gain 7? Lots of students here think like, oh, I can just fill that shell with 7 electrons. It's a lot of negative charge. What do light charges do? They will repel, right? Light charges repel. So it's much easier to lose that 1 electron. Atoms will always do the path of least resistance, right? They're lazy. So it's much easier to lose 1 electron than to gain 7. So it's going to lose that 1 electron. Now when it loses that 1 electron, right, loses that, actually I'm going to just draw an X here. Let's grab a different color. Let's grab a different color here. And it's going to lose that 1 electron. Now when it loses that 1 electron, how many electrons will it have now? It will have 10 electrons. And how many protons?
11.
Still has 11. Remember, protons determine what your atom is. So if it has now 11 positives and 10 negatives, how many more positives does it have than negatives?
1.
Just 1. This means that this sodium ion now has a charge of positive 1. So it's Na+. We do not write 1s in chemistry just for saving space. So wherever you do not see a number, it is the number 1. So it'd be Na+. Now when I'm drawing an ion, often we will put it in square brackets, and we will denote the charge up top like that. But that's the reason why it has a positive charge. Protons don't change. We are changing the number of electrons. Let's look at a different element. Let's look now at chlorine. How many electrons does chlorine have?
17.
Has 17, right? What does chlorine want to do?
Gain 1 electron.
It wants to gain 1 electron. Now, when it gains 1 electron, which noble gas does it now look like? Which noble gas does it share the same electronic configuration as?
Argon.
Yeah, it'll be the same as argon. So we are always trying to look like our nearest noble gas, right? We want to be stable just like them. So, when sodium chloride makes a ionic bond, this chlorine here is going to get an electron, right? sodium lost one, this chlorine here is going to gain one electron. And when it gains that electron, right, because originally our chlorine had how many protons?
17.
It had 17 protons. How many electrons in the neutral atom? The same. And then when it became an ion, right, when it became an ion, how many electrons does it have now?
18.
It has 18 electrons, which means that what will its charge be?
Negative.
It will be -1. Good job. Does that make sense? So we have 17 protons and we have 18 electrons, which makes our charge a -1. So that positively charged ion of sodium is electrostatically attracted to the negatively charged chloride ion, and they form an ionic bond together. So if we were to look at a crystal of sodium chloride, for example, so a crystal of sodium chloride would have this repeating structure, right? We have a repeating structure here, where the purple balls here represent your sodium and the green represent your chloride ions. So when you get these big uniform crystals of table salt, effectively at the atomic level, this is what you have. You have this lattice of positive attracted to negative, attracted to positive, attracted to negative. Does that make sense? And those ionic bonds are simply just that electrostatic attraction. Now, let's explore a more complex example. Because sodium chloride is really easy to understand, right? It's just one electron lost, one electron gained. But not everything is that simple. Not everything is that simple. Let's look at perhaps one of the elements from the second most reactive group on our periodic table. What's one of the second reactive groups, second most reactive groups? Carissa?
Magnesium. Or
Yeah, alkaline earth metals. Magnesium is one of them. Sure, we can do magnesium. So if we look at magnesium, how many valence electrons does magnesium have? How many?
2.
Yes, it has 2. What does it want to do?
Lose 2.
It wants to lose those 2 electrons. So if we look at magnesium, magnesium here has how many electrons in total?
12.
Has 12 electrons in total. And it really wants to lose those 2 valence electrons. Now, someone give me an element. Actually, no. Let's use one of the halogens. Somebody give me a halogen here. Any of the halogens. Sure, fluorine. I like fluorine. It's nice and easy to draw. How many valence electrons does fluorine have?
7.
It has 7. Right, in the previous example, sodium gave that electron to chlorine. Now we have a slightly different scenario. We have this magnesium here and this fluoride, well, it's not an ion, yeah, this fluorine atom. How many electrons does our fluorine need to receive in order to be happy, to be stable? 1. So if this magnesium here gives this electron to our fluorine, right, we lose this electron here. Our fluorine is now happy, right? We've gained an additional electron. And by gaining an electron, what will the charge on this fluorine now be? Yeah, it'll be negative 1, right? So our fluorine now will have a charge of negative 1. But is our magnesium happy? Why not? Why not? Why isn't our magnesium happy?
It still has one electron in the outer shell.
Excellent. Yeah, it still has 1 electron in its outermost shell. So how do we get rid of that other electron? Yeah, we need another element. If we're reacting magnesium with fluorine, what is that other element going to be? Yeah, another fluorine, right? So if we add another fluorine here, we can get rid of this electron from magnesium. And now is everyone happy?
Yes.
Correct, right? Our fluorines here both gained an electron to get a full shell, right? They're both negatively charged. And our magnesium has lost 2 electrons. How many protons does our magnesium have? 12. Right? It has 12 protons right over here. Has 12 protons. How many electrons does it have now?
10.
It only has 10. So what is the charge going to be on our magnesium?
Positive 2.
Sorry?
Positive 2.
Positive 2, excellent. And this is a little weird thing we do in chemistry. We write the number before the charge. It has a 2 positive charge. One thing about ionic bonds, the way I've drawn it like this, is their charges always need to balance out. How many positives do we have here? 2 positive. How many negatives do we have?
2.
We have 2, right? So the number of electrons donated and received needs to equal out. Let's do one more example. One more quick example here. Now, we're going to find there's a much better way of doing this. Right now it's a little painful because we're drawing out full Bohr diagrams. But we will learn Lewis dot diagrams, which is much more simple representation. And then eventually we're going to use just math to figure it out. But for now, it's going to be pretty tedious. We are just going to be using these Bohr diagrams. So, what if I said I had aluminum and let's say oxygen. So aluminum oxide is what we're going to be making. Oh, by the way, I'm not sure if you saw these a lot last year. Who here remembers counting atoms from grade 9? Not a single person? That's fine. The chemical formula for what we just did, the first one, we had 1 sodium, 1 chlorine, so it was just NaCl. The second example, we did magnesium fluoride. What do you think the chemical formula for that is? Yeah, we don't write the positives and negatives in our chemical formulas, though, so that'd be MgF2. That was the chemical formula for the second one, right? For every magnesium, we need 2 fluorines. Now for this last example, what we're going to be doing is looking at aluminum combined with oxygen. So what does the Bohr diagram for aluminum look like? How many electrons am I going to draw? How many electrons are there in aluminum?
13.
How many?
13.
Yeah. There's 13. So, our aluminum here has 13 electrons, and this is our aluminum. And how about our oxygen? What does our oxygen have?
8.
We have 8. So, look here. Our oxygen has, let's do this in blue. We have 8. This is our oxygen. So what does our aluminum want to do here? What does our aluminum want to do?
Lose electrons.
Yeah, it wants to lose electrons. How many does it want to lose?
3.
3. Why doesn't it want to gain 5? Because that would also give it a full shell.
Because it's harder.
Yeah, it'd be less electronically stable, right? We add all that negative charge. Whatever the least number of steps is what your atom is going to do. So here the least number of steps is to lose these 3 electrons. Now, how many electrons does oxygen want to lose or gain?
It needs to gain 2.
Excellent. It needs to gain 2 to have a full outer shell and be happy. So this aluminum here, we're going to donate these electrons over to our oxygens. Right, we're going to donate these electrons over to our oxygens. Is our oxygen now happy?
Yeah.
Oh, it is, right? Our oxygen's happy. We now have a full outer shell. And what is the charge on our oxygen going to be?
Negative.
Not just negative, it's going to be
-2.
-2, right? We've gained 2 negative charges, right? If I have to go back to that example, how many protons does oxygen normally have? Well, not normally, but how many protons does oxygen have? It's 8. How many electrons does it have now?
10.
Has 10, right? That's 2 more negatives than positive. So we have a charge of 2 negative on our oxygen ion. Is our aluminum happy?
No.
Why not?
It needs to lose 1 electron.
It needs to lose 1 more. So what do?
Add another oxygen.
We need to add another oxygen. So if I add another oxygen here, we can get rid of this electron on aluminum. Now we X-nay that electron on aluminum. Now is aluminum happy?
Yeah.
Yes.
It is, right? Aluminum is now happy. It has a full outer shell of electrons. Right? We've lost these 3 electrons, now it has a full outer shell of 8. And as a result, what will be the charge on our aluminum ion?
Positive.
Yeah, it'd be 3 plus. Right, so our aluminum here, since we've lost 3 negatives, we had originally how many electrons and protons?
13.
We had 13 and 13, and then we lost 3 electrons to give us what? How many? 10. So now we have 3 more positives than negatives, which makes this a 3 plus ion. It's a 3 plus ion. Alright, so our aluminum's happy. Is our oxygen happy though?
No.
You can see this is going to get messy pretty quick. So what do we need to do to make our oxygen happy?
It needs to gain 1 more electron.
Yeah, where's it going to come from?
Another aluminum.
Another aluminum. Right? It's going to come from another aluminum. So you can very clearly see why we need a better model than using Bohr diagrams, because is this a pain in the butt?
Yeah.
Yeah, this is not a good time to draw all this up. But it is great for understanding that full shell, right? You can clearly see when we lose these 3 electrons, we now have a full outer shell of electrons. So this aluminum atom is going to donate this electron over here to oxygen. Now is this oxygen happy? Yeah. So this oxygen ion has now a full shell, electronically stable, and is super happy. Is this aluminum atom happy though? It's not. What does it need to do?
Lose 2 electrons.
It needs to lose its final 2 electrons. And where is it going to donate them to?
Oxygen.
It's going to donate them to 1 more oxygen. This is the last time we're ever going to do this, by the way. It's going to donate it to this oxygen atom down here. And now is everyone happy? All of our atoms are happy now, right? Our aluminums both have a 3+ charge. Our oxygens all have gained 2 electrons a pop to get full outer shells, and they each have a 2 negative charge. In total here, how many electrons were donated and received? Too many? Yeah, way too many. I agree. I agree. This is a pain in the butt to draw, but 12?
6.
Gonna be 6, right? Just count 1, 2, 3, 4, 5, 6. So that's why we have a 6+ charge in total and a 6- charge in total if you add it all up. So again, when it comes to these electrostatic interactions, these bonds that form these ionic bonds, the total charge does need to balance out. This idea will be very important when we move from models to math. And that's where students often struggle, moving from kind of the concrete to more the conceptual. So next class, we are going to be learning about Lewis dot diagrams. And the class after that, we're going to be learning about the math of ions. And that lesson is often where I lose students. So it's really important that you do practice right now working with these Bohr diagrams, and you can clearly understand where these charges are coming from and why is it that this has a 3+ charge, for example. So help me out here. If I was going to form a bond with, say, nitrogen, an ionic bond, what charge would nitrogen have if it were to make an ionic bond? Think about it. Nitrogen looks like... How many valence electrons does it have? It has 5, right? So then, how many more or less does it need? It needs 3 more negatives. Therefore, what would the charge on nitrogen be? 3 negative. How about the charge on phosphorus? How many valence electrons does phosphorus have? Has 5. So what would be the charge on phosphorus? 3 negative. Are you starting to see a trend here? So all of the elements of a family share the same what? They share the same number of valence electrons. Does that mean that they're going to have the same charges when they form ionic bonds? Yes, right? If we look at our different groups here, it's a little kind of cheat sheet for you when we start talking about the math of ions. Our alkali metals, what charge will they always have? +1, because what do they want to do? They want to get rid of that 1 valence electron. Right? They want to lose 1 negative so they become positive. How about your alkaline earth metals? 2 positive. They will all have a 2 positive charge because they want to get rid of those 2 valence electrons. Now what about the boron group here? Really this only applies to like the first 2 elements, but what about the boron group? Boron and aluminum. What do they want to do? Sorry? 3 positive, right? They want to get rid of their 3 valence electrons to get a full outer shell. What about the nitrogen group? We just talked about it. They have 5 valence, 3 negative. Now we flip the script. It's easier to lose 3 electrons than it is to, it's easier to gain 3 electrons than it is to lose 5. Okay? What about the chalcogens, the oxygen group? Not 3 negative, 2 negative. Remember, oxygen has a 6 valence electrons, therefore wants to gain 2 negatives, 2 electrons, and all the members of this group have a 2 negative charge. What about the halogens? 1 negative. And lastly, what about the noble gases? None, right? They don't really make bonds. And why don't they make bonds again? They're unreactive. Why are they unreactive? because they have a full outer shell of valence electrons. That is the reason why atoms form bonds. So I'm going to highlight that and put a big asterisk beside it. I talked about it yesterday, I talked about it again today, but it's the driving principle behind everything we learn about in regards to bonding. So, just a quick reminder here, atoms form bonds in order to get a full valence shell, right? A full shell of outer electrons. And why do they do this? Because this makes them stable, electronically stable, just like their noble gas neighbors, right? Atoms form bonds in order to get a full valence shell, which, by the way, this is my shorthand for which, I use W/C, which makes them stable. Another way of saying this is they want to look like their nearest noble gas. They want to have the same electronic configuration as their nearest noble gas. That is the driving principle behind ionic bonding and covalent bonding. All right, so last quick note. The formula for that compound we drew was Al2O3. Now, this here is what we call a formula unit. Okay? So last year, you may have heard the word molecule kind of used for everything. Do you guys remember what a molecule is? Yep.
Two or more.
Atoms that have been bonded together. Well, with ionic compounds, we don't use the word molecule because, as I showed you, that big crystal of sodium chloride, right, it's this repeating unit structure. It's not just this one molecule floating around. So the smallest unit of an ionic compound is a formula unit. And a formula unit here of aluminum oxide would be 2 aluminum ions and 3 oxygen ions.